And now it's my pleasure to introduce our three speakers. First, we'll hear from Dr. Barb Cohen, who is a planetary scientist in our Solar System Exploration Division and a returned sample scientist for the Perseverance mission, among many other roles. Our second speaker will be Giovanni Rosanova, who is the chief of the Sounding Rockets Program Office at our Wallops Flight Facility. And last but not least will be Gerrit Everson, chief of the Aircraft Office at Wallops. And so with that, we'll go ahead and get started with Barb.
Thanks, Laura. Travis, would you start with the Missions to Mars video, please? We're going to start off with a brief history of the missions that NASA has sent to Mars over the last several decades, so that you get a flavor for how we're building up to the Perseverance mission.
Hey, there we go. There she goes. Yeah, that's data.
There is some sort of a hacker to the data, and we have now full confidence that this does indeed correspond to a photograph of Mars.
Preliminary analysis of this data. Can you describe what you see on Mars?
Yes, it's there.
By the extraordinary men and women of NASA and our Jet Propulsion Laboratory. Right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity will stand as an American point of pride far into the future.
I just wanted to call and say congratulations to the entire Mars Science Laboratory team and really all of JPL. You guys should be remarkably proud.
Let's go to the title slide then, please. So that's kind of a whirlwind tour of what we've been doing at Mars. My name is Barbara Cohen. I'm in 698, which is planetary science. I'm a planetary geologist. And what that means is I have an undergraduate degree in geology, my planetary science degree, my PhD, and I look at rocks on other planets. And we take them apart to learn about the history of a planet. We learn about what made the rock, what the conditions were on the surface at the time those rocks were made, how old they are, and what they tell us about the history of the planet and its future. And I'm very lucky to have been involved in the Mars exploration rovers, where I joined as a participating scientist, and I worked my way up through the ranks and eventually became an associate PI for that mission. I'm currently on the Curiosity science team as we're exploring Gale Crater. And as Laura mentioned, I'm a return sample scientist for the Perseverance mission. And I'll tell you a little bit about what that means as well for the samples that may come back to Earth, we hope. Next slide, please. NASA's Mars exploration program is built around follow the water. That's something that you may have heard a lot. We discover water on Mars quite a few times. Actually, every time that we discover water on Mars, what we're really doing is we're learning a new aspect of the Martian water cycle. Of course, on the Earth, we have a very complex water cycle. Water exists in our atmosphere, in our rivers, our oceans, in our own bodies. All of those things are sources of water and sinks of water, and the water comes and goes, and that creates our water cycle. Mars doesn't have a water cycle quite as complex as the Earth. However, water is locked up in the rocks. It could be locked up in water underneath, water ice underneath the surface, certainly in the polar caps of Mars. And so water is one of the things that is one of the basic ingredients for life as we know it. So as we're searching for life beyond the Earth, as we're searching for life's origins, how did the solar system form and evolve to be able to give rise to life on Earth? Water is one of those things that's a common thread. And that served us very well for Martian exploration. It makes us understand the geology, how those rocks are put together, what Mars is like now, what it was like in the past based on the rock record. It serves to help us understand Martian climate. The Martian climate is very different from the Earth, but we probably had a very similar history. So why did the two planets diverge such that the Earth is very clement? We have very nice weather most of the time, maybe not these last 2 weeks in DC, but in general our climate is very clement and habitable for life. But on Mars it's very cold and dry now. What was it like in the past? What caused our climates to diverge? Of course, we're looking for life outside of the Earth. We're trying to understand not just whether life exists or whether life could exist, but what are the conditions that really can give rise to life? Are they really unique to the Earth, or is that something that could happen in many places in our solar system, our galaxy, or our universe? Are we alone? And of course, preparing for human exploration. Mars is our horizon goal for human exploration. We'd really love to send people there to do some field work as a geologist, to learn and to live and work on another planet, and to be able to colonize our solar system, as some people want to do. And so learning about Mars as it is now and what it was like in the past really helps us prepare for human exploration of Mars. So that's our exploration program. Next slide, please. And we've been very successful at NASA and with international missions now. You may have just heard that both the UAE and China successfully launched Mars missions in the last several weeks. And Perseverance will be the third one this year to launch to Mars. These are all of the successful and not so successful Mars missions that have been flown. Viking and Pathfinder were really about what was Mars like in the past. What were those rocks like? And what are the conditions now? Viking was the first to tell us about the Martian atmosphere as it is now. It was the first to tell us that Mars is cold and dry now. But in the past, when we look with missions like the Mars exploration rovers and Phoenix and InSight, we're looking at what Mars is like now, but also what were those rocks like in the past. Can we open those up and read the history of the planet in those particular locations and say, this is what Mars was like, this is how it evolved? Curiosity, of course, which is operating now, is telling us about whether there are building blocks for life on Mars now, on the Martian surface. So the sample analysis at Mars Suite, which is a Goddard instrument on Curiosity, has detected methane coming out of the surface. And that tells us something about the way water is interacting with rocks and interacting with organic materials. They've also detected organic building blocks of life in those rocks with the SAM instrument. So that's telling us a little bit about the organic chemistry and about the interaction with the surface now. And that helps us understand what conditions may have been like for those organic molecules or more complex molecules like we need for life. And Perseverance is going to go a step further and really look for biosignatures. And that means things that could only have been created by life. Now, this is a really challenging mission for Perseverance. So we have an interesting payload, and we'll also bring back samples to accomplish that. Next slide, please. So the Perseverance mission objectives include both geology and astrobiology, and also sampling and preparing for humans. It's very much following our template for Mars exploration that's been so successful. We are going to be exploring an ancient environment on Mars. It's a deltaic environment where we think a river emptied into a crater. We'll talk more about that in a minute, and understand the processes of water interaction with rocks. We're going to assess the habitability of that environment. We know life on Earth likes water. If we have water and rocks and energy, is that something where ancient life could have arisen? Maybe it's not there now, but could it have left traces of itself behind? So we're seeking evidence of that past life. And we're seeking places to sample, that is to bring samples back to our state-of-the-art laboratories on the Earth to assess both the geology and the astrobiology potential of those samples from Mars. We're also carrying instruments that will tell us about the current environment, the temperature, humidity, wind, and dust. And we're carrying an instrument that's actually going to pull oxygen and water out of the atmosphere and condense them in an instrument to understand how we can scale it up for production of human in situ resource utilization on Mars. Next slide, please. So our timeline shown here, of course, launch is coming up next week. It'll be Thursday morning, early our time at about 7 a.m. our time. It will launch on an Atlas 541 and have about a 7-month cruise. Of course, our Mars missions launch every 2 years to take advantage of the alignment between the Earth and Mars. Mars comes around every 2 years to Earth's 1 year. So every 2 years, the planets are very close to one another in their orbital period, and we can launch on very short trajectories, like 6 to 7 months, to get to Mars. So we'll arrive in February of 2021. The entry, descent, and landing, you might remember the 7 minutes of terror from Curiosity. As we'll see, the Perseverance rover is built on a very similar chassis to Curiosity, and it will land in much the same way. So it will have the parachute coming out and the retro rockets and dropping off the rover, very similar to the 7 minutes of terror. But there's a couple upgrades to the system, and the most important one is terrain relative navigation for precision landing. So our landing ellipse is going to be very much smaller than what we saw for Curiosity. For the surface mission, we're expecting 1 Martian year or 2 terrestrial years, or 1.5 Martian years, 3 terrestrial years, sorry. And we're expecting 20 kilometers of traverse capability in our prime mission. All of our missions to Mars have exceeded their nominal lifetime. That doesn't mean we count on that, but that's something that we look forward to. Next slide, please. The Perseverance rover itself, like I said, is built on the Curiosity chassis design. In fact, we had to extend that out a little bit to accommodate some of the new instruments, but it's very similar. You can see Curiosity on the left, Perseverance on the right. They're very similar. There's a couple key differences. We have different instruments, so we're asking different questions of our mission, and so we need different instruments to answer those questions. We'll talk about the instruments later. We have a much heavier arm. It's much more capable. It's much more rugged. Our arm is what drills the samples to cache them for future return, but our arm on Perseverance also has two really important instruments on it that it has to position and hold in place. So we needed a beefed up arm. And we have new wheels. If you go to the next slide, please, you can see the difference between the Curiosity wheels and the Perseverance wheels. Of course, this is something that has made the news, is that the wheels on Curiosity have started to crack because they are carrying so much weight over some really rugged terrain with sharp rocks. And so the new wheels for Perseverance learned those lessons. Those wheels are a little bit thicker. They're narrower and thicker, so they're going to hold the same kind of weight, but they're a little bit narrow and a little bit thicker. And you can see the tread design, rather than having angles that encourage breakage, they're a little bit curved for the terrain gripping. Next slide, please. Perseverance is also carrying the Intrepid helicopter. So let's take a look at a video with the helicopter, please.
Sometimes you have to do something just to show that you can do it. When the Wright brothers flew for the first time, they flew an experimental aircraft. And in the same way, the Mars helicopter is designed to show that we can fly powered helicopter flight in the Martian atmosphere.
From day one, this was the unwavering dream of our team, to get our helicopter launched to Mars so that we can get that opportunity to do that very first rotorcraft flight test in the actual environment of Mars. It's extremely difficult to fly at Mars because the atmosphere is so thin. Compared to Earth, at Mars it's less than 1%. So the first and foremost challenge is to make a vehicle that's light enough to be lifted. And then the second is to generate lift. The rotor system has just been very fast. 2,000, 2,200, 2,400, 2,600. We're spinning between 2,000 and 3,000 revolutions per minute, and it takes a lot of energy. So it's that balance of a very light system, yet having enough energy that's needed to, spin the rotor so fast to lift, and on top of it, having to design in the autonomy.
It has to be fully autonomous from the time it takes off to the time it lands. What we do on the ground is we plan the flights, and so we determine from here where we want the helicopter to go.
Our experiment window is 30 Martian days. So we have planned up to 5 flights of incremental difficulty.
Very first flight, the main thing is we want to get the legs off the ground, and so we will basically go up about 3 meters, and we'll hover there, and then we'll come down again, and that will be the first, really major milestone.
Most of our flights will be at the 3 to 5 meter height. We will be going horizontally again at a few meters per second, probably go out, 50, 70 meters and come back. In successive flights, we'll probably push that further, try to go further. So our priority will be to get back engineering telemetry and not so much images, but I'm sure we'll return a few, because they'll always look cool.
At this point, we've tested all we can on Earth. We have mathematical models that shows how it'll fly at Mars, and we've tested it in the simulated environment that we can create on Earth. It really is time now to do the real flight tests at Mars.
Nothing is a given, but we have done everything we can in terms of a test program here on Earth. The vehicle's performing extremely well so far. It's been doing exactly the right thing, even right now, when it's bolted onto the Perseverance rover. So there's a very good chance that we'll pull it off, yes. But it's still high risk, and none of us forget that you could have a glitch that, could mean end of mission, yes.
It's going to be exciting, reacting to any surprises we have. We can't wait. What's really most important is everything we're learning here is for the future rotorcraft systems that we want to introduce into space exploration.
Fantastic. So that tells you a little bit about the Ingenuity helicopter. I know there's a couple questions about that, so I hope that answered some of them. We will not be using the helicopter to plan traverses for Perseverance on this mission. It's not planned that way. And that's because the helicopter is a technology demonstration, but it is a technology demonstration of what it could help us plan in the future. So given what we're planning to do, it's going to be in the first 30 days of the mission. We'll fly that helicopter a couple times, scout out some areas and see how they help us plan the initial traverse. But the helicopter will not be flying with us the whole time. Maybe in the future we'll have helicopters or other aerial vehicles that can help us do that. Okay, so let's talk about the landing site, Jezero Crater. Jezero was selected because it is a crater that has an ancient deltaic environment. What that means is that there is a crater that formed, it's about 4 billion years old. It formed in very ancient terrain on Mars. And then it was filled in. So the topography of the crater has a flat floor, and it's shallower than we would expect for a young, fresh crater on Mars. And that means that it's been filled in, probably with sediments. We don't know the origin of the sediments, if they're blown in, or if they're water lane, or if they're fallout from a volcano. We don't know the nature of those sediments yet. That's one of the things we're hoping to find. But one thing we can see on the left of Jezero Crater over there, where you see Lower Inlet Valley, there's a little river or a sinuous valley there that we interpret as water formed, possibly a river or a creek or an outflow that flowed into the crater itself, and it created a fan. And then there's an outlet channel on the other side. So we think that water flowed into the crater, eventually filled up the crater, possibly created a standing lake, and when it got high enough, it broke through the other side and flowed out. That's our current geologic interpretation of Jezero Crater. On the next slide, I'm going to show you a close-up of that delta. So here's the outlet, or sorry, that should say inlet channel, not outlet channel, my mistake. That says inlet channel, there's your fluvial sinuous rill coming in from the left, and you can see it spilling out on the right-hand side. The color code here is different minerals. So what we see here are minerals that are made by water, including things like sulfates, evaporites, and salts. And so we think that this environment was a rich one for water interacting with rock and leaving behind traces of that water-rock interaction. On the next slide is an example of a delta coming out from an Alaskan glacier. And this shows you sort of the analogous situation on Earth, where we have a river that's coming down from a high point, and as it spills into an open area, the water slows down. It may turn into these braided channels, and when it does that, it doesn't have the carrying capacity for sediment anymore, and it drops all the sediment that it was carrying into these alluvial fans. These are really great places to go look for the interaction of the water and the sediment in a low energy environment that's traditionally on Earth very conducive to microbial life. We see things like stromatolites or biomats, algae, things like that. Love this kind of environment. And in fact, in this picture where you see those greens and oranges, those are all microbial life forms on that delta. So this is a very rich environment, a lot of nutrients, water, and a quiet, conducive environment that we want to explore on Mars and see if the similar situation was in fact on Mars when this delta was formed. The next slide, please, shows us the payload that we're going to be using. Now, I told you before this is a little bit different. It's a lot different from the Curiosity payload. They're all new instruments, and they're different because they have different functions. We still have a panoramic camera on a mast. That's really crucial. That shows us where we are, what we're looking at. The scale of this, of course, is something like a Mini Cooper. So it's a little taller than I am, but I'm a short human. But this panoramic camera gives you something like you would see if you were standing at the outcrop. It's about as high as a person, and it gives you a stereo view, just like you would have with your eyes. So we still have that. It's got an extra zoom capability right now that we didn't have on the last ones, where we can zoom into really close-up views. Also up in that camera is SuperCam. That's an extension from ChemCam, which is in the Curiosity rover. SuperCam also uses laser-induced breakdown spectroscopy like ChemCam does. It shoots a laser out into the rock. It ablates the rock and it measures the light that comes off of that ablation plume. It breaks that light down into a spectrum, and that spectrum tells us about the elemental composition of the rock. So SuperCam also has a LIBS capability, but it also has a near-infrared spectrometer, which tells us about the mineralogy of a sample in reflected light. And it also has what's known as a Raman spectrometer. A Raman spectrometer is when we send a laser beam with a lower energy, not enough to ablate it, but enough to excite the molecules in the rock. And certain molecules will absorb that light and fluoresce it back in a different wavelength. And that tells us about the molecules themselves, the spacing between them, so that it absorbs those wavelengths of light. That Raman spectroscopy is really very good for organic molecules in particular. So we're sending out UV laser in SuperCam, we're sending out a green laser, and in the Sherlock instrument that you can see on the arm, that's also a Raman spectrometer, and it's sending out a UV laser. And so between the two of those wavelengths, they're exciting organic molecules, and we'll be able to get a picture of those organic molecules just from the excitation of them. We also have on that arm, while we're out there looking at Pixel, there's a Watson camera that's a micro imager, and Pixel, which is an X-ray spectrometer, a micro X-ray spectrometer. So Sherlock and Pixel get put out on the arm, and they get very, very fine resolution on the rocks where we put those down. So between those, we get mineralogy and elemental chemistry, a very fine focus on the samples. On the end of the rover, you can see on the left-hand side, the part that sticks out, that's our RTG, that's our energy source. And in the belly of the rover, we have RIMFAX, that's a ground-penetrating radar. And so we're going to be using that as we go along our traverse to understand the layers that we're driving over. If there are any dielectric constants or permittivity changes under us, possibly due to water or different kinds of rock, we'll be able to pick those up. And then finally, you see MOXIE, and that produces oxygen directly from Martian CO2. So it pulls in the atmosphere, refines it, and produces oxygen. And that's our extension for human Mars exploration. We also have a weather station. NETA is our weather station that tells us about the current conditions on Mars. Right now, there's a web page where you can go for Curiosity and see today's Martian weather. We'll have the same thing for Perseverance. Next slide, please. So when we talk about biosignatures, these are the kinds of things we mean. This is how we're going to be looking for ancient life signs, not just the physical and chemical things like we think of like fossils, stromatolites, but also minerals arranged in a specific order, organic molecules, and isotopes. All of these can be considered biosignatures, and that's what our Perseverance payload is really geared toward. The next slide, please, tells you about my role on Perseverance in more detail, which is about the sample. So I'm a returned sample scientist, and what that means is I'm heavily involved in choosing the samples and how we're going to choose the samples that Perseverance will collect for future return. My expertise is in samples from the moon and Mars and asteroids and meteorites. And this is a couple photos of the Apollo samples, us working with the Apollo samples in my laboratory. And the one on the right is, you may have heard, we opened up a new pristine Apollo sample. Those Apollo samples that were collected more than 50 years ago keep on giving. We still have requests for them. There are hundreds of samples, new samples that get worked on every year all around the world. Those samples told us about the formation of the moon and the formation of the Earth-Moon system, the conditions that were in our solar system, and people request them even now, 50 years later. They are truly the gift that keeps on giving. So our understanding of planetary science is going to double when we get samples from Mars. Next slide, please. This is how we're going to collect samples. On the left-hand side, you see the little sample tube. You see how big these are. They're about 1 centimeter across. They're going to be about 10 grams of sample. That doesn't sound like a lot, but for terrestrial laboratories, that's more than enough to do multiple analyses on. So we can look at isotopes, we can look at the ages, we can look at stable isotopes, biosignatures, anything that you want to do to these samples we'll be able to do in terrestrial labs. And the way that we collect the samples is by depot caching. And what we mean by that is the rover will go around to the different outcrops, and it will pick up samples and it'll drop them at specified places called depots. The rover's not going to hold on to the samples because if anything happens to the rover, that'll happen to the samples as well. So we're going to drop them off as we go, encased in their little cases like you can see on the left, and those are aluminum cases that will be hermetically sealed. So they'll be sealed up and they'll be left on the surface, and then our caching rover is going to have to go get those in the future to pick those up and return them to Earth. Next slide, please. Based on what we know about Jezero from orbital missions already, these are some of the example samples that we might be able to get when we get there. Now, of course, our understanding is likely to change once we land, but based on what we know already, we think that we can get typical floor material. We think there might be a lava flow there. If we see a lava flow, we'll definitely want to collect that and see how old it is. We think there's some olivine and carbonate bearing units. It's an unusual combination on the Earth, but we see that in a couple places on Mars. So we really want to understand what that means for Mars. It could be an unusual type of lava flow, or it could be something that was initially formed with mafic minerals like volcanic minerals and later altered by the action of water to things like carbonates. We don't know the difference between those right now, so we'd be excited to pick up a sample and see what that means. And then we get into, of course, the delta. The delta is where we want to look for biosignatures. Even if we don't see them with our rover instruments, that doesn't mean that they're not there. That means that we should pick them up and bring them to Earth and really carefully take them apart. So we've got samples that we will pick up from the delta. We've got things that like our typical regolith or typical dust. Dust is something that encompasses the whole planet. It's homogeneous over the whole planet. We may need to understand that better for human exploration as well, to understand how to design our filters. So picking up a regolith sample or a soil sample, including that dust, is going to be an important one for us. We think that the river that flowed into Jezero may have ponded and formed a lake. So we have some samples that we might want that are related to that formation. So channels, lake deposits, point bars, these are related to the flow of water and the action of water within Jezero crater. And then in our extended mission, if we get outside of Jezero crater into that ancient terrain, we might want to pick up some of that as well and understand the ancient terrain the crater formed in. And importantly, we have blanks. Those tell us the action of the rover, any microbes that we carry with us, anything that the rover does to the samples, those blanks are going to be able to tell us. So those are really important return samples. The next slide, I'm not going to talk about this in great detail, but suffice it to say that NASA and ESA are working hard on a plan to return these samples to Earth. We don't have dates for these missions yet, but hopefully in the 2030s, we'll see these come back to the Earth. And finally, Travis, if you would play the last movie, our launch, like I said, is July 30th. That's this Thursday. So I'll leave you with this video of building and getting ready for launch.
so much, Barb. That was a great overview. Our second speaker is Giovanni Rosanova, who's the chief of the Sounding Rockets Program Office at Wallops.
Okay, good morning, everyone. Thank you for joining us. And I just want to say that the Wallops Flight Facility, especially the Sounding Rockets program, is very proud to have contributed to this mission, and we're very excited to see it finally launch. So the Sounding Rockets program was approached by our friends at JPL a few years ago to provide a test platform for the parachute design. And as you can see in the slide, the payload on the cart there has a bulbous section that houses the test parachute, and then the rest of the payload is our support subsystems, telemetry, attitude control, to help get the data down and to orient the payload on reentry. And the unique color pattern of purple and gold was picked by our friends at JPL so that make the payload easy to find in the ocean upon recovery. And so that became a sort of a signature image of the payload. We launched 3 sounding rocket missions to test these parachutes, and the first mission was a baseline of the concept of operations. It was a low loading type of mission on reentry, and then the subsequent missions were increasing the loads on the parachute upon reentry and improving some of the material properties on the parachute, and that was all taken care of by our friends at JPL. And so this endeavor was not just the Sounding Rockets program here at Wallops, but also a lot of support from our launch range here. The infrastructure, the launchers, the recovery effort was executed by our friends here at Wallops in the launch range. So now, Travis, if you can cue up the video that shows the overview of the mission.
High above the eastern shore of Virginia, a rocket is hurtling through the atmosphere at nearly twice the speed of sound. Attached is a 3,000-pound payload that is designed to test a parachute for Mars. On board, a computer is calculating the altitude and speed to determine the precise time that it will signal to deploy the parachute. These aren't the first tests of parachutes for Mars. 50 years ago, NASA began lofting parachutes to altitudes and speeds meant to simulate the conditions of Mars entry. Those early tests demonstrated the challenges of inflating lightweight materials in a 1,500-mile-an-hour wind and having them survive well enough to help enable a safe landing on the red planet. Today, as our missions become ever more daring, we need new parachutes capable of surviving those strenuous environments, and we need ways of testing them at loads higher than ever before. To make those tests a reality, engineers at NASA's Jet Propulsion Laboratory worked with NASA's Wallops Flight Facility to develop a new test technique. The Advanced Supersonic Parachute Inflation Research Experiments, or ASPIRE project, uses a 2-stage Black Brant 9 sounding rocket to carry its payload to the conditions needed to stress the parachute. The rocket is launched out over the Atlantic Ocean and ascends to altitudes where the atmosphere of Earth mimics the atmosphere near the surface of Mars. The third and final ASPIRE test launched on September 7th. The parachute was deployed at nearly twice the speed of sound. In less than half a second, 200 pounds of nylon, Kevlar, and Technora go from a small drum-sized bag with the density of wood to an inflated parachute with the volume of a large house, generating nearly 70,000 pounds of drag. Here, in slow-motion images, you can see the rapid emergence of the parachute as it begins generating the drag crucial for deceleration at Mars. These images give us amazing insights into the physics and early behaviors of a supersonic parachute inflation. The apparent ease of the unfurling and unfolding in the parachute belies the severity of the extreme environment in which this occurs. Awaiting below were a recovery team who had retrieved both the parachute and the payload and returned them to shore. The parachute was then meticulously rinsed and hung to dry before inspection. Miles and miles of thread and over 3 million stitches are used to hold the parachute together, and we will examine each stitch. After 3 successful tests of ASPIRE, NASA has now tested their new parachute at loads and conditions exceeding any large supersonic parachute before it, and 40% higher than the highest load expected for the Mars 2020 mission. Our parachute is now certified for flight at Mars.
Okay, so again, Wallops, we here at Wallops in the Saturn Rockets program and at the range are thrilled to have contributed and provided 3 successful test flights of the parachutes for this mission. And we achieved that by tuning the ballast in the nose cone that you see in the forward end of the payload and the launch angle to get the desired velocity profile on the down leg of the parabola during the suborbital flight. So the missions were so successful that we've already been approached by our friends at JPL and Marshall Space Flight Center to do suborbital demonstration missions for other parachutes, larger parachutes, and other mechanical systems for the future Mars sample return mission. So we're happy to partner with them again, and we look forward to continued success. And now I'll hand it over to Gerrit Everson, the chief of our aircraft office, to talk about recent support that was given for the Perseverance team.
And good morning, everyone, and thanks for the introduction, G. As Giovanni and Laura stated, my name is Gerrit Everson, and I'm the Chief of Flight Operations at Wallops Flight Facility. And for those of you that are not aware, the Wallops Aircraft Office operates a fleet of aircraft that are used to support NASA's scientific and research initiatives. So currently we're flying a P-3 Orion, which has been our bread and butter in the science world since 1991. And we also operate a B-200 King Air. And then we also operate a C-130 Hercules. So I'm here to tell you today about the role that the C-130 played in the Mars 2020 Perseverance mission. So first, a little bit about the C-130. It's a large 4-engine turboprop aircraft that's capable of carrying a payload of 42,000 pounds, and that puts its maximum takeoff weight at about 155,000 pounds, so a pretty big aircraft. The range is dependent upon the cargo capacity, but it's in excess of 2,500 nautical miles with a moderate weight payload. So most recently, we've used the C-130 to support scientific missions such as ACT America, that's atmospheric carbon transport across America. But right now, we're actually using it to support a parachute airdrop testing program for the commercial crew program. So in that regard, we're flying out to Yuma and releasing 10 to 15,000 pound test payloads to test the strength of risers that will be used on reentry vehicles. But in early April, the aircraft office was contacted by the Mars 2020 Deputy Project Manager, Matt Wallace, with an urgent program need. And Matt needed to ship 5,000 pounds of flight hardware from the West Coast to the East Coast to meet a critical launch deadline of this summer, so a pretty big deal. Now, if you remember back to April, the pandemic was in its early stages, and there were some big programmatic concerns. One was obviously the safety and health of the security and support staff to do a surface shipment. Additionally, businesses were shutting down, so such a surface shipment would be at risk. So Matt asked us if it was possible to fly the Wallops C-130 to Palmdale, California, pick up the cargo payload, and then fly it to the Kennedy Space Center to meet the launch deadline. So fortunately, we were already in a configuration where we could support simple roll-on, roll-off operations for cargo with the commercial crew program. So from our perspective, the request was rather straightforward, and we were able to put together a proposal on short notice to fly a crew out to Palmdale, pick up the payload or the cargo, and then fly it to the Kennedy Space Center. So on March 10th, our C-130 crew departed Wallops for Palmdale. And upon arriving, they immediately refueled and then unloaded the cargo. And of note, this included the sample tubes that will be flown to Mars, returned with soil samples, returned to Earth, and may tell us for the first time whether life existed on a planet other than our own. So the next day, the C-130 crew departed Palmdale for the Kennedy Space Center, and after a 7-hour flight, successfully and safely landed and offloaded the cargo. So after nearly 8 years of development and thousands of flight shipments, this event provided the final piece in the path to launch. So I've been at NASA for 7 years, and this is the first time that I can recall a Wallops aircraft being used to fly flight hardware for such a high-profile mission. So I'm proud of the support that the Wallops team was able to provide, particularly Code 830, and coming together and providing support to the agency during a very critical time. So Laura, I'll hand it back to you, and certainly welcome any questions from the audience. So thank you very much.
All right, well, thank you all so much for your presentations. Those were awesome, and it was really cool to hear about the variety of roles that Goddard has played to help Perseverance get to the launch pad and be ready to go for a successful mission. Thank you also to the audience for the questions that you have submitted. Again, if you have any more, you can put them in that link there below the video player in Ustream. A couple of these were answered during the presentations from our speakers, so I'll try and focus on questions that I don't believe were answered, or at least not elaborated on in a lot of detail. And so with that, the first question I'm going to ask is, since we're collecting and storing samples in Jezero Crater, does this mean there's a good chance that this is where we'll also land the first astronauts on Mars?
No, it doesn't mean that necessarily. The point of the Perseverance mission is to be looking for ancient life in a habitable environment that is not the same as what humans will need for their first explorations of Mars. I think we're looking more at places at clement landing sites that are safe and that also have access to water ice below the surface. So that is more where the human exploration program is looking. But climate across Mars is going to be very applicable no matter where we measure it. And so that's going to be very applicable to human exploration.
Great, thank you. Let's see, we have a couple of questions about the Ingenuity helicopter, but I believe most of those were answered largely in the video that was shown. Next question I'll ask is, how will the collected samples stay protected while resting on Mars, but then also while eventually being returned at some point?
The samples are enclosed in those sample tubes. They have multiple layers of tube material, and I'm sorry, I don't know exactly what all those materials are. I do know they are designed to be able to stay on Mars for indefinitely because we don't know when they will be picked up and returned. When they are collected, when they are drilled and collected, the collection mechanisms will be able to see the sample, to confirm that it's in the tube, and then to seal the sample. So there's a hermetic seal to prevent sample material from leaking out or even volatiles from leaking out. And then it will be put on the surface and those areas will be marked. So they are designed to stay on the surface of Mars in a reasonably good condition for decades.
Great, thank you. The next question will be for Giovanni. The question is related to testing the parachute, and the video that you showed covered a lot of the different aspects that were involved in trying to simulate conditions and Martian conditions and differences between Earth and Mars. So I'll reframe the question to say, what was the most difficult constraint to try and mimic or model or test on Earth?
Great question, great question. The most difficult thing was deciding when exactly during the actual flight to deploy the parachute. So predictions, you can have all kinds of predictions and you have your standard deviations. You don't know exactly when you're going to pinpoint that dynamic pressure, the desired dynamic pressure to give the 70,000 pound load that was the ultimate goal. And our engineers on the Sounding Rockets program put a smart system on board with GPS tracking to calculate the actual velocity during reentry and the attitude, and decide on its own when to deploy the parachute at the optimal conditions. So that was the toughest thing, but it was achieved quite nicely.
Great, thank you so much. Our next question I think will be for Barb again. So how do you think the world will respond if we do find evidence for past life on Mars? And how might that also influence our scientific and human exploration of the rest of the solar system?
It's a really great philosophical question, and one that I'm sure we would all love to sit down and debate over coffee sometime. I think that many people think the search for life is one of the greatest pursuits that humanity can undertake. Are we alone is something that philosophers have wondered about for centuries, if not longer. So Personally, I don't know the answer to that. I think that it would spark certainly a lot of scientific interest. It would tell us a lot about not just Mars itself, but about the way our solar system functioned and about the prospects for other solar systems maybe arising in the same way. We had a similar kind of sparking of interest when there was potentially life in a Martian meteorite. You may remember that from some years ago. That turned out to be perfectly explainable by non-biogenic processes, but you could see kind of how that went and the interest that that sparked. So finding life on another planet would be revolutionary for a lot of scientific disciplines. How that would be meaningful to you, only you would know.
Great answer. Thank you. Let's see. Our next question is, how significant was the Hellas impactor in the transformation of the ancient Martian climate?
Ooh, that's a lovely question. Those impacts, Hellas and Isidis, big basins on Mars, is something that we've wondered a lot about scientifically. We know that there were also big basins on the moon that may have radically altered the moon. So those big basins on Mars may have been part of an ancient heavy bombardment, and they may have contributed quite a bit to outgassing from the Martian interior, but then conversely sending a lot of material away from Mars and possibly stripping water that may have already been there on the surface or in the atmosphere. So the short answer is that we don't know. I wish we had a time machine where we could go look at the before and after of some of these impacts. Perseverance is going to a crater that formed in that ancient terrain that was stirred up by the Isidis impact. If we can get to outside of Jezero crater and find some of those materials and return them, that may give us some insight into the effect that those large basins had on Mars.
Great, thank you. There's interest in the Mars helicopter shirts that the JPL crew was wearing in the video. Are those available?
JPL actually has its own online merchandise store, so you can go look on the JPL merch store.
Great, yep. And I know that the Goddard store, the online store, has Perseverance t-shirts for anyone who's interested. All right, so next question. Why is it less risky for a later rover to collect and carry the samples than for Perseverance to do the same?
That was an engineering trade that was made as the missions progressed. I think the initial idea was to keep all the samples with the rover and then attempt to hand them off in like a canister from one rover to another, or to put the canister directly on the Mars return vehicle. I think that the complexity of the sample collection and caching system was one consideration. But another consideration was that the canister approach would mean that we would not be able to use the Perseverance rover in more potentially risky situations for fear of getting stuck there and not having another rover be able to come in and do the sample handoff. So we typically don't send the rover to very risky situations, but as the mission moves on and we get more familiar with its capabilities, we may want to do that. And especially if we saw something like a dinosaur bone or a shell, or I'm being facetious, but if we saw something that we really interpreted to be a biosignature, and we needed to put the rover in a difficult or tricky situation to reach it, that would probably be worth it. But we don't want to endanger all of the samples that we've ever collected to be able to go after those potentially risky samples. So that's why we are using this depot approach, where every few samples that we collect will cache together, and then we'll have to send a rover to pick those up. So it's, each approach has its pluses and minuses.
Great. Well, we are at the top of the hour, and I do want to be respectful of everyone's time. And I know other people may have meetings or lunchtime coming up. So I think we'll go ahead and end here for today. But thank you to all of our speakers. Thank you to everyone who tuned in and watched. Thank you again, Travis, for running and producing this behind the scenes. We really appreciate it, and go Perseverance. Let's all stay tuned for hopefully a great launch and then eventual landing next February. All right, thank you everyone. Have a great weekend.